Okay, welcome everyone to today's CDAC webinar, our first of 2023. This is in fact our 77th webinar in this series that we started back at the beginning of the pandemic, and we've continued ever since. Today's speaker is Kurt Leinenweber from the School of Molecular Sciences at Arizona State University. Kurt is well known in the field of high pressure geoscience for supporting and further developing and applying multi-anvil large volume press experimentation. And this talk is going to be a review of sorts of that. And it's especially timely because Kurt is the PI of a new mid-scale effort funded by NSF to build a major facility in this area. And he'll tell you about that today. Kurt has a bachelor's from Brown University in geology and a PhD from Princeton, also in geology. He was a postdoc at the University of Tokyo, a research assistant professor at Stony Brook before moving to ASU in 1994, where he's now a research professor. So Kurt, we're looking forward to this talk. Over to you.
Thank you. Thank you, Russ. And hello to everybody. Let me share my screen again and get the talk started. Okay, well, my talk, I kind of gave it a pretty big title. It's Science from the Multi-Anvil Press, Past, Present, and Future. What I'm really going to talk about is a subset of that, which is going to be a little bit of history of what just basically what a multi-anvil is, how I view the definition of a multi-anvil, and a little history of the development of multi-anvils. I know a lot of people here already know a lot of this, but I hope some people find something new, and also it's one of my favorite topics, so I can't help it. And then some of the research highlights from my work with multi-anvils in terms of scientific results. I'll go through those quickly, and then I'll talk about the COMPRES cell assembly project and the new FORCE initiative that's located at ASU. And Russ, what's the length of this talk? I got to keep an eye on my time.
Generally 45 minutes to 50 minutes, so we can have time for discussion.
Okay. All right. So so first of all, multi-anvils are one of my favorite things in the world. I first learned multi-anvil from Eiji Ito and Misasa. I was sent there by Alexander Navratsky, who was my graduate advisor, and I had a fantastic time. And I couldn't even sleep at night because I was so excited about it. And back then, there were very few of them, and it just seemed like no end to what you could do with them. And I think that's still true, although now there are quite a few more and a lot more people working with them. I guess that's a good thing. A lot more results, and it's something I support. I wish everybody had a multi-anvil in their garage, but anyway, so basically a multi-anvil is a high pressure device that is somehow designed to apply force to objects from more than two directions. That's how I define it. Even though when I look up multi in the dictionary, it just means more than one. But usually these devices that have only one or only have two anvils are called, there are diamond anvil cells, Paris Edinburgh cells, and Drickemer cells are the really common examples of those. They call them, I'll just call them opposed anvil devices. This example here is, I believe it's the Paris Edinburgh cell at SNAP, and correct me if I'm wrong, it's just a photo I found on the web. So first, another very important industrial device is the belt apparatus, which I also would not call a multi-anvil, even though it has these side, it has two pistons, and then it has this support from the side. But even though it has that support, I still wouldn't really call it a multi-anvil because it's got only two pistons pushing from opposite directions. And the other one is just for containment. And this is the first device that was used, by the way, to make industrial diamonds back in the 50s by Tracy Hall and others at General Electric in Ohio. And I've been to that factory and worked with Sami Malik and Emil Stoyanov there on several projects. And they don't have the original belt apparatus. They scrapped it. I wish they hadn't done that, but they still use belt apparatus, bigger ones, for their industrial processes. The first actual multi-anvil device ever made, when Tracy Hall left GE, and you can read about this in Robert Hazen's book. There's a whole lot of great stuff in there called The Diamond Makers. But when Tracy Hall left GE, he wasn't allowed to use the apparatus that they had there because it was all, well, I guess he had signed an agreement not to do that. So he had to invent a new device, and he invented this tetrahedral anvil device, which has 4 separate pistons, and that was really the first multi-anvil device that I am aware of in history. And what we'll find is that these devices are based on they're all the really successful ones are based on platonic solids. So this is the smallest platonic solid is a tetrahedron, and then we're also going to see devices made with octahedra or cubes in various combinations. The reason for that is because you can push in equally on all the faces of a platonic solid, and it will remain stationary. So therefore, you can put force on all the faces, and that's really what makes pressure, force per unit area on the face of some kind of medium, pressure medium as we call it. He also here he is with the second press he invented at Brigham Young University, where he had moved from GE, and it's a cubic press. So that's another platonic solid, and it just has 6 rams pushing from 6 directions. And there it is. And then later I'll talk about dia devices, and that's actually an octahedron pushing on a cube. Well, I'll show a picture of that later. And then I also said, why not try another one? It would be interesting to know if these two, the icosahedron and this one, if devices could be made with those, because the pressure actually increases with each step in this sequence. The only problem with these is it might be a kind of a machining or a technical technically difficult to put equal forces in all directions on these shapes. And then when in geosciences, when we needed more pressure, so diamonds can be made, can come from as shallow as 150 kilometers, but to study the 450, the 670, and the top of the lower mantle, this device was invented by Kawai and Endo, the 6/8 multi-anvil device, and that's actually the most popular device for sort of workhorse, large volume, high pressure. Here's a picture of what, this is a great picture taken by Anne Pommier, who's actually at Carnegie now. She was at ASU for a little while, and then went to Scripps and then Carnegie. You probably know her. This is a beautiful picture that she took with this red light. I really like it. And it shows the octahedron pressure medium, the octahedral pressure medium inside of what will be 8 carbide cubes that are pushed equally from 6 directions. So the 6 directions are the first stage, and we call this the second stage. And this has 4 thermocouples, or 4 wires, 2 thermocouples, because she's doing electrical conductivity, and she uses them both as thermocouples and as electrical leads to do her measurements. There's some of her data shown next to it. So that's the kind of thing you can do with the multi-anvil quite easily. possibly compared to a diamond cell. You can get uniform, very uniform temperatures for very long periods of time, for days, if you want. And you can do measurements like electrical conductivity. You could also grow crystals, which is what I do a lot of, and I'll show some examples momentarily. And you can have a large space for buffers, and to give away the ending, with our new force project, we're actually going to get a larger multi-anvil, a 6,000 ton multi-anvil, and it's basically a size advantage to get even more space and be able to do more things. And I'll just very briefly say that the multi-anvil and the diamond cell together were a great combination for discovering all these major mantle minerals that we all know and love, like ringwoodite, Wadsleyite, ringwoodite, bridgmanite, which was actually found in a diamond cell first by Liu, and this ilmenite, which is akimotoite, and all these great phases. A stishovite actually was found earlier, and I think he used some kind of belt device for that. So here's some quick examples of some of the work we've done at ASU over the years, and I even threw something in that I did at Stony Brook before 1994. So I'm sorry for showing some old stuff, and I'm just basically showing my favorite results, old or new. When I first came to ASU, we had a very talented student named Hervé Hubert working for Paul Macmillan. He did a lot of great stuff with boron and carbon and nitrogen and oxygen, looking at a lot of potential material, super hard materials. He found some new materials, and he had Lawrence Garvey doing eels. So it was a great study, because a lot of times it's hard to study these light elements. But if you're doing eels, in addition to simply X-ray diffraction and the normal, then you can really tell what's going on in your samples. One of the neatest things he made were these icosahedral particles, which here they are in microscope view. This is B60, and it's a semiconductor, so it's got this red color. It's a wide bandgap semiconductor, but it has some color, and it's based on a boron forms an icosahedron, and he wasn't trying to do this, but when we tried to grow single crystals in B203 flux, so B203 melts, and then excess boron forms B60, boron suboxide. And what happened was that the crystals, unexpectedly to us, formed icosahedra, and Mike O'Keefe was fortunately on the project and just looked at it and said, oh, it's McKay packing. And this is what McKay packing is. It's packing of spheres into an icosahedron, but in this case, it's actually packing of icosahedra into an icosahedron. Here's some more pictures. This is a SEM picture of one of the nice icosahedral particles. What it really is B60 is rhombohedral, and it has a rhombohedral angle of 63 degrees. So it's quite close to the interior angle of an icosahedron, and therefore they can twin. It's actually a compound of 20 twins that form an icosahedron. It's interesting, and now it's also been observed now for B4C, and even though these are small crystals, there's new papers where instead of using B203 as a flux, they've used boric acid, H3BO3, and they're able to grow crystals up to 1 millimeter, and they're still icosahedral. And instead of 5 GPa, they've gotten it down to 1 GPa. The real motivation for this would be that these particles could be great for grinding. That would be a commercial application, because grinding actually it's preferred to use obtuse angled edges and corners in grinding because they don't break easily, and that's why, for example, diamonds, which are one of the most important grinding materials, are grown as cube octahedra, which are shown here. because they last longer. The corners don't break off during grinding as quickly, and all the commercial diamonds, if you grow diamonds at a low temperature, I hope I get this right, you get octahedra at a low temperature, cube octahedra in the middle, and cubes at high temperature, or vice versa. I'm sorry, I should have checked that. But so they grow it in intermediate temperatures to get these cube octahedra. So these, you could imagine, especially B4C, which is a very important grinding material, but also B60 potentially could be used as a grinding material. They're all super hard. B4C is the third hardest material, at least the third hardest commonly used material after cubic boron nitride and diamond. Okay, another discovery we had at ASU, accidental discovery, I would say, because we were trying to grow zeolites at high pressure. Ulrich Hausermann is a chemist, a solid state chemist, or he's an inorganic chemist who's got really good instincts for projects, but was trying to grow some kind of porous materials at 9 GPa. But even at low temperature, like 400 degrees, 300 degrees, we were getting stishovite, which you could never get without water. Stishovite, you need at least 800 to 1,000 degrees to make stishovite from coesite or quartz or glass, SiO2 glass. We were very surprised to find stishovite at such a low temperature, but then even more surprising, the peaks were shifted a lot. And it just was, especially the peaks involving the A-axis. And Christina Spector, who did the work and who's now in Europe at working at the beamline over there, Christina Spector thought there was something wrong with the X-ray machine. So we tried another X-ray machine and got the same result. Turned out that the stishovite had taken on weight percent quantities of water. That was totally surprising. And we couldn't even imagine how that water could fit into stishovite. You know, there's really no room. This is a stishovite structure, and there's no room. It's a rutile structure, edge sharing octahedra, very small spaces in between. So where would the water be? But eventually we figured out that it was a silica vacancy with four OHs on it. And it was basically like a hydrogarnet substitution, but 6 oxygens instead of 4. And hydrogarnet substitution is substitution on a tetrahedron in garnet. This is hydrogen substitution on octahedron, but it's 4 hydrogens. So they have to bond to 4 of the oxygens. And here we put them on the bridging, on the edge sharing oxygens. They haven't been located, but we've done calculations. Dan Shim has done calculations. We've done a lot of work on this since then. And this leaves these 2 oxygens underbonded. So the strong hydrogen bond is to these 4 oxygens, but then it probably has a hydrogen bond to these as well. And that's evidenced in spectroscopy and NMR as well. And also these distances were consistent with NMR, the distances between the hydrogens. And here's the TGA support. This is another nice thing about a multi-anvil. I mean, since then, there's been some great diamond cell work on the hydrostishovite at the beamlines, but this is actually the best way to get water content, thermogravimetric analysis, which was done at Davis in Navratsky's lab by Emil Stoyanov. And you can see this is anhydrous stishovite, and then you can see the percents get up to, in these samples at 9 GPa, 3 weight percent or more water. So this is a very thirsty stishovite. Here's a picture of coesite. This is glass. This is coesite forms first at low temperatures, and then after the coesite forms, stishovite forms, but it crumbles off of because of the volume change, it crumbles off of the grain and winds up, well, actually these look clumpy, so these didn't crumble, but some of it does. And since then, the diamond cell work by Lin at Geophysical Lab and Neser at ASU found much more water, and in particular, I was involved with this work with Neser, and we would decompress each sample after laser heating and look at the zero pressure lattice parameters, and that's where we got our water contents. And we got up to 7 or 7.5 weight% in our laser heated samples from anything over 30 GPa, basically. So just out of reach of typical multi-anvils, but soon I think we'll be able to make, or us or somebody else will be able to make high quality samples. The other thing about this stishovite is it forms as a calcium chloride structure, even at 30 GPa with the water in it. And that's low for calcium chloride, but with water, it is stabilized. And when you recover it, it is back to the rutial structure. So it goes from orthorhombic to tetrahedral during decompression. And I'm not sure how the crystal quality is. I mean, we get a powder pattern, but so far our peaks are not always narrow. And I don't know if we can get narrow peaks on any of these samples. Okay, so looking at my time, I'm going to move along. I just want to talk about this. This is actually work I did at Stony Brook before 1994, but it's also one of my favorite projects that I've ever been on. And it started with work on FeTiO3, where Siono had discovered the lithium niobate or corundum phase. He called it corundum, but it's actually lithium niobate. But it turns out it's perovskite at high pressure, and that's work I did at Tokyo University to look at that in a diamond cell and find out that this is actually perovskite at high pressure. So we thought, well, Alex Navratsky was thinking calcium, iron, maybe if we reacted them together, we could get the mother of all perovskites, is what she called it, which I thought was a funny term. So we did that, and we didn't find a solid solution like we were thinking. Now that I think about it, the sizes are quite different. We found ordered phases in between. So as far as the FeTiO3 end member, it was Siono that called it a corundum, and turned out lithium niobate. They look very similar in X-ray. And I now realize Siono discovered this material. We were back then, in that sort of thing of it was one of my first studies. So anyway, all I'm saying is just because something is not strictly right doesn't make it wrong. And in the end, it turns out that lithium niobate phase, the quench phase of perovskite, has been found in nature very recently. And it's very nice to work on something that is eventually found in nature. That's a good feeling, especially when at the time people are like, why are you working on that? That's one of the questions I heard a lot. It's called Wang Daodayite. I hope I'm pronouncing it right. And it was discovered in a meteorite. So it's the lithium niobate phase of iron titanate. And we also have other phases in this system, and I have hopes for these being found in nature. So far, they haven't, to my knowledge. But these are the phases that I made on this join. It was calcium iron titanate with this stoichiometry with 1-to-1 calcium to iron, and then one with 3-to-1 calcium to iron. And the iron in this one is in square planar coordination, which is quite surprising. But there are 4 other atoms, other oxygens, not that far away. So it's really kind of acoordinated. Oh, sorry, that's a little fuzzy. Anyway, this phase is a Maurizio compound with IA bar 3 symmetry. It's cubic, and you see the tilts of the octahedra. It's a minus in the Glaser terminology. It's a minus, A minus, A minus. It's a rotation about the 1-1-1 axis of a cube. And that winds up bringing 4 oxygens very close to the iron. So it becomes square planar. That's what that little, and there's the gray or the perovskite octahedra, the titanium octahedra, square planar. And then all the iron is the same in this. And it's recently been found, it's still of interest, and it's recently been found to have giant dielectric properties. And I'm not going to try to define what that is because I'm not an expert, but that was nice to see. Oh, here's a better picture of it. That's the square planar there. Square planar iron and the titanium octahedra. And then the other one we found was a unique perovskite structure that had never been seen before. It has a space group P42 over P42 over NMC. It's tetragonal. P42 over NMC tetragonal, and it turns out it's a kind of a twin of that other phase I just showed you. So you get half of the iron in tetrahedral coordination, which is that red tetrahedron. There's the titanium framework, TiO6 framework, octahedra, and then here's the square planar iron, but in this case, it's a little off the center. It's not acentric though, but it has centers of symmetry in the structure, but this particular atom is off the center of the square a little bit. Okay. So I'm going to just show a couple of slides about the COMPRES project, and then I'll talk about force. The COMPRES project is a project all the way back to 2004, where we did community development of multi-anvil assemblies, and we had all along we've had 5 different sizes of octahedra, which is how we basically make different pressures and different volumes. The largest is this 15 millimeter edge octahedron that we use with 25 or with wait a second, 2515. It's a 25 millimeter edge, and we use it with 15 millimeter cubes. Then we have this 18 millimeter, and then 14, which is a 14.8, and then 10, 10.5. 10, the two numbers refer to the octahedron edge length and the carbide truncation edge length, and then the 8.3. And so the pressure ranges would be, this is at least with 1,000-ton multi-anvil, which is the typical size. This goes to about 6 or 7 GPa. This goes to 11, 14, 20, and 25, and high temperature. Here's the calibration. We provide calibration curves, but we still recommend people do their own calibration because presses can differ. And we've supplied thousands of assemblies per year now to the multi-anvil community. And to tell the truth, right now we're having, especially with force coming online, it's getting hard to keep the supply chain going. So people are waiting longer for their orders. We're trying to fix that. But basically, it's been a huge success in terms of popularity and people being able to get their labs up and running, and also interlaboratory consistency, which was our original hope. The original hope was interlaboratory consistency and sharing of information. It wasn't always easy to get people to share a lot of information about their assemblies, but once you create a whole series of assemblies that a lot of people use, and all of a sudden the communications just open right up and everyone's using the same assembly. Okay, so now I'm going to talk about force. And force is this, it means Facility for Open Research in a Compressed Environment. It's located at ASU, and it's an NSF mid-scale project that was funded in September. This funding started in September 2021. So it's been going for more than a year. I hope I'm getting the dates right. I'm sorry. I should have written it down here. Does anyone know what? Okay, never mind. So this started with meetings of COMPRES, and COMPRES was an extremely important community thing, and it had so many results, including this and including other things. And I would say even the idea now that there's a beamline COMPRES like organization now that's going to be on beamlines. It's going to focus on beamlines. This was a great COMPRES, for at least for me, and I think for a lot of other people, was a great thing. And I hope that the flavor of COMPRES continues. We had a meeting in Colorado Springs where we had a big one-day breakout session, and we talked about the needs for additional high pressure, more modern or more capable high pressure devices and apparatus that people could use in a common laboratory that would be somehow made open for visitors. And one of the things that I realized at this meeting was we couldn't do it all with one instrument. We were all talking about a 6,000 ton press, but when you heard what people wanted, there were several instruments needed. And so I'm going to talk about that. So here the PIs on this are myself, Alex Navratsky, Dan Shim, Tom Sharp, and David Smith. And we have an internal advisory committee of somebody from engineering, Seth Tongay, and Rick Hervig, who's a SIMS expert at ASU. And then our outside personnel are Carl Agee, Pam Burnley, Gabriel Gonmesia, Anne Pommier, and Yang Bin Wang. And we just had a workshop where four of them came and visited, and Anne was in France. Anne Pommier was in France for holiday. And we've hired two new people. We've hired Kyusei Tsuno from Rice University and Kara Brugman, and they are research scientists. And Kara is also going to be involved in outreach. And we're looking for a new faculty now who's going to be in SMS, School of Molecular Sciences. That search is currently ongoing. Who's going to be possibly, maybe you'd call it the scientific leader of force in the future. And it's going to be an open facility, as I said. And we're going to go for large samples, single crystals, and pressure and temperature conditions over a wide range. And all the equipment is somehow new to the United States. And we're also have programs for grads and undergrads. And well, let me tell you about the four pieces of equipment. There they are. So these are the base. We had some visits to Germany, and I just flipped through pictures of that, but decided to move on. Maybe show you later if you want. We decided on purchasing this a 6,000 ton press from Sumitomo, which is already it's like the one in Ehime. This is the picture of the one in Ehime. It's called Bochan. Ours will be called Ichiban. That was our name for it. It'll be a different color. But Ehime has been so successful with this press, and it's functioning so well that and also the timeline was of a certain length, so we went for that press. We were also looking at a Vogenreiter 5,000 ton press, similar to the one that's that's just been installed in China at Wuhan. And that's one of our pieces of equipment. The next one is so this is for ultra large volume. Actually, I'll show what it's for in a minute. The next one is this this dia type press, which is what Katsura. This is a picture of Katsura's press in Bayreuth, and it's very good with going to ultra high pressure, and a torsional device, and also a 6.89 kilobar IHPV gas vessel. So the 6,000 ton press basically makes larger samples and has a larger sample volume. So you can either make very big, this is the definition of big, and multi-anvil is a centimeter, or half a centimeter. These kinds of nanopolycrystalline diamonds that Irifune grows need about 15 to 17 GPa and 1700 degrees. So they're not just made in the diamond stability field, they're made much higher. And that's because there's no flux. Diamond is normally grown with iron as a flux or something like iron. So this shows how large the volume can be. The cubes are bigger. The cubes get up to 75 millimeters. That's what was used for these. So that's what we're going to have, and that's what people will be able to come and use, and we'll also develop things like FO2 buffering and other things that require a lot of space for the samples. So Jasmine, the application is it's an octahedron out here. Basically, that's an octahedral cavity that pushes on wedges that push on a cube. And it turns out that the side forces are not quite the same as the top and bottom forces because of the sliding geometry and the flexure of these blocks, these big blocks on the outside. This cube is your basically your carbide cubes or sinter diamond cubes. So what Katsura did, which is quite clever, is hollowed out the top and bottom to make them softer. So there's actually an opening inside there. And by doing that, he could use more brittle carbide without breaking it as much. So here's some of his pressure calibrations, and this is the normal multi-anvil. This is just with harder carbide and no other particular modifications. And then this is with tapered anvils. It's getting up to 60 GPa. We talk about a megabar. Sinter diamond has been taken over a megabar in Japan at Spring 8, and you could also do that here. Although, anyway, that it's expensive, so that's hopefully there's a way to do it without breaking a lot of sinter diamond in the future. So that's a tapered anvil, like I mentioned. This is how the taper is. Katsura. Actually, Ito developed that in Misasa a long time ago, but this is a different, well, it's pretty much the same as what Ito was doing when I was there to make perovskite, but now using harder carbide and using this specially aligned geometry. So the first one is the uniaxial, and this is what that geometry looks like from the side. And it's basically two axes pushing, and the somewhat uneven forces, so you can't do the ultra high pressure with it. This is the 6 axis with the forces equalized on all 6 axes, so that you can do high pressures without breaking the anvils. Twister is really going to start off being for physics. We have David Smith is a physics professor who's one of our PIs, and he has 20 years of experience with torsional devices. And so we have a torsional device, and we'll create novel samples for TEM studies. It can induce phase transitions and other phenomena. Temperatures are fairly low right now. They're 200 or 300 degrees Celsius, but we plan to work on furnaces that could make this go to a higher temperature and be applicable in geology as well. And then the gas vessel. Gas vessels have come a really long way in Europe, and you know, a lot of Americans don't use gas vessels as much, but it fills a gap from 0 to 1 GPa or 0 to 0.7 GPa, where you can have extremely accurate pressures that work on very large samples with very, very uniform temperatures. So we are filling that gap by having one of these, and we expect to attract a very different group of people, volcanologists and people like that, which would really enhance our outreach to the community. Okay, I'm going to finish up because it's almost time. Here's this little summary of the pressure volume capabilities that we have. And at low pressure, I didn't put the gas vessel on here. It would probably be similar to the industrial presses. Then we have the the large volume in blue. This is the 6,000 ton press. I wrote 5,000 here because at that time we were thinking about a different press, but it's actually a 6,000 ton press. This is the 6-axis press with carbide and then 6-axis with sinter diamond. Here's a little map of the lab. Ichiban will be in the middle, JASMINE over here, Twister over here, which is a torsional device. JASMINE is the dia, Ichiban is the big press, and then the gas vessel. We have places for people to work. We have a chemistry lab. We have a glove box for air sensitive samples. And this is under construction. I'll show you a timeline in a minute. We'll also have office space, and including office space for visitors and for our staff, and a conference room. And ASU is doing this. This is also upcoming in our new location. Here's the milestones from our project manager, Steve Wynn, and it shows all the dates that we expect things to be done. So you can think about, and this is a implementation project, which means we're doing implementation. We're building the lab in 5 years, a 5-year period. Anyone who's interested in sort of coming and helping with that, doing testing the devices, people that are really into the nuts and bolts can come anytime, but then there'll be the times when the presses come online as research devices, and then people can come and do research on them. We have undergraduate, and NSF emphasized that they wanted us to train construction engineers as well as scientists. So we have one construction assistant who's these are, and then we have another one, Isaac Roden. So we've had 2 so far. We'll have a lot more than that soon. Now that the construction is about to happen, it makes sense to bring on construction people. We have hourly workers. The other ones were interns. That's those 2. And now Isaac Roden has transferred over to hourly. We'll have summer undergrad research experience, grad participation. We'll have 2 PhD students and summer schools. We've just had a workshop. Later on, the workshop was basically Zoom with people from ASU Live. We had about 30 people from ASU, 30 people from or 40 people outside ASU on Zoom. We hope, or we're not, we hope, we expect that we'll have workshops in the future when the lab is actually on the ground, where people will want to come and actually in person give talks and see the lab. So that's basically what we're doing. It's 12:45, so I'll give you guys a chance to ask any questions you have. Thank you very much.
Thanks very much, Kurt. Very nice talk. Congratulations on your success in launching this really interesting facility, this unique facility for the country and the community.
Thank you.
Questions, just unmute yourself or put a question in chat or raise your hand. Maybe to get this started, what kind of user program are you envisaging in a little more detail? You'll have on-site users like a beamline. You'll have scientists that actually do experiments for users. What is the plan?
Yes, that's a topic of huge discussion. We have a weekly meeting with the 5 PIs and the project manager, and that's one of our big topics. What we envision and what we want is similar to a beamline. People would come here with their own travel if they can, and then so the travel would be the responsibility of most visitors, although we also hope to have some travel assistance for certain outreach purposes. And then the experiments themselves, we will seek funding to run it like a beamline, where people really don't have to worry about large expenses, which will be associated with the big cubes and the other aspects of this project. We're talking about how to seek that money, and we need to start seeking it quite soon because it's only 3 years until we go online as a facility, and we need to be on the ground by then.
Great.
And sorry, and like I said, we will have office space and other things, and then people. It's not only the presses and the devices, but ASU has a huge array of other techniques that people can use to analyze their samples, or to either create starting materials or analyze samples.
Mm-hmm. Okay, Priscilla from Los Alamos, you have a question?
Yes, well, first, thank you for the very nice talk, and I'll likely be a user in your facility, so this is really great.
Glad to hear it.
Since you have this slide up, I'm just curious for why you guys decided not to go with the German furnaces.
To build what?
Why you guys decided to not go forward with this particular model in your facility?
Which model?
The German one, because you have the.
Oh, the German one. Oh, yes, the Vogenreiter.
Yes, because you're on this slide now, so I was curious.
Oh, sure. Actually, we are buying our dia from Vogenreiter. And we were looking at Sumitomo and Vogenreiter for the dia as well as the large press.
Okay.
And it was just a decision we made, just based on including delivery time and some other factors. That the delivery time on the Sumitomo was much shorter. Okay. It was within the 5 year, easily within the 5 year. We would be able to have it delivered and have it, and it has to go in the lab first because it's going to be in the way of a lot of other things moving in. Mm-hmm. So there were certain reasons that weren't even quality or any of that kind of consideration.
Yeah, that was my question. If there were some technical reasons, or if
no,
it's just, yeah, okay.
Very good question, and it's important for me to say that we considered the devices to be equivalent in quality. Mm-hmm. We couldn't see any difference in that aspect. Of course, the one in China hasn't. I don't know how the situation is now, but it was delivered right before the pandemic, and so it hasn't actually been running yet. Mm-hmm. They still have to do the rest of the setup, but I'm not up to date on that. That information is probably a year old, so I don't know. Does anyone know anything about the Wuhan press from Vogenreiter, whether it's okay?
More questions, comments? It was nice seeing the review of some of the earlier work, and I haven't followed the water in Stishovite story, but how much water or hydrogen can you put in Stishovite, and how does it change as a function of pressure, going to very high pressure before Stishovite transforms to the Pa3 or the pyrite-like structure? Do you know?
Great question. What actually happens in detail is, so Stishovite itself, not the calcium chloride form, but the normal Stishovite form that's tetragonal, can take a couple of one or two weight percent water, and it gets more and more water rich with pressure up to about 30 GPa. And then when the calcium chloride phase appears at 30 GPa with a lot more water, about 6 or 7% water at the first appearance, then the Stishovite, as you increase pressure more, the Stishovite actually becomes less water rich because the water is going into the calcium chloride. And that goes up to 55 GPa, where even the dry stishovite is calcium chloride, right? As you well know. So then that phase, the calcium chloride phase, our diamond cell results with the shim group, where we accurately measure the water by decompressing and measuring the room temperature lattice parameters, was 7.5 to 8 weight percent, I believe. 7.5, let's just say 7.5, not quite 8. And that was the maximum that we got. And then at 60 GPa, another phase appears that I didn't mention. I should have, but it's even more water rich. It's a nickel arsenide, disordered nickel arsenide phase. And it's even more water rich. Then we don't know the water content because it's unquenchable, but it's more water rich than the calcium chloride just based on phase diagram considerations. And then after that, at higher pressure than 60 GPa, the calcium chloride also starts losing water because of this other phase. We have not gone as high as we haven't gone over a megabar.
I see.
So we don't know what's next in that phase diagram.
Thanks.
And by the way, there's a great study, from Carnegie on that hydrous stishovite as well. But yeah, that nickel arsenide phase was unique to Carol Neeser's study. She found it during her her explorations.
Well, there were questions early on about it being thermodynamically stable, whether it was just a kinetically stable phase. I don't know if that's been sorted out, but
that was the discovery of that phase by Vitaly Prokopenko, and he was working on dry stishovite, but there may have been some water in his sample. It is thermodynamically stable in our laser heating.
okay.
It's very, very persistent in a saturated system, water saturated.
Vitaly's online. He may want to comment.
Yeah, I don't know, Vitaly, do you have any comments on that? He actually discovered the nickel arsenide form first, and he even told us he saw the pattern and said, "I bet it might be the nickel arsenide." So that certainly helped.
Okay, more comments or questions? Okay, if not, thanks very much for a really nice talk.
Thank you.
Overview, and I think I'll look forward to working with you in various.
Thank you, and likewise.
Terrific.
Thanks very much.
Thank you all for joining us.